Alright, this video is about nuclear chemistry, specifically being able to tell the difference between radioactivity, fission, and fusion. It's also about how these technologies impact our modern life through nuclear power plants, nuclear weapons, half-life, and all sorts of other things. Alright, the first thing you need to know is a little history. Radioactivity was discovered when uranium was being photographed. Black cloth should prevent light from getting on photographic plates and therefore exposing the photograph. But the uranium was somehow giving off some sort of light that could go through the black cloth that people couldn't see, but that showed up on the image. That was called radioactivity. We now know that radioactivity is made of the particles and rays given off by an unstable nucleus. So here's the nucleus and atom, and here's the electron cloud around it, and the nucleus contains protons and neutrons. Well, it ends up that if you have the wrong ratio of protons to neutrons, normally it should be about 1 to 1 or up to 1 to 1.5. And if it's not that ratio, if it's not the right ratio, then the nucleus spits out particles to try to stabilize itself. Those particles are usually high energy, and if they hit cells in your body, they can cause cancer, cell damage, other sorts of things. The particles are alpha particles, beta particles, and gamma rays. Alpha particles are nothing more than a helium nucleus. Essentially, the atom spits out 2 protons and 2 neutrons together in a package, and that makes a helium nucleus. By the way, all helium on Earth actually comes from this process. We mine helium out of the ground. It's really actually old alpha particles that have gotten the 2 electrons and therefore aren't dangerous anymore. Beta particles can also be spit out. These don't cause as much damage, but they're high energy electrons. The really bad ones are the gamma rays because they can go through almost any sort of material except for lead or thick concrete, and they cause a lot of damage to cells. They're high energy light, so they can go through the air really easily. An important thing to know about all this radioactive stuff is that when these particles are spit out of the nuclei inside the atoms, it actually changes the atom's atomic number and mass, and that will actually change the element. It's called transmutation when it changes the element. When those particles are spit out, the atom eventually stabilizes itself by ejecting all those particles and just ends up as a regular old stable atom, no longer radioactive. You should know the penetrating power of these things, that alpha particles can be stopped by skin or paper. Beta can be stopped by a little thicker shielding, but luckily they're not as dangerous as alpha particles or gamma. But gamma goes through almost everything except for lead or concrete. Here's a little information about the effects of radiation on the body. Essentially, it'll target all sorts of things and cause DNA damage. And obviously, DNA damage is a bad thing, causes cancer and maybe even radiation poisoning, which leads to much more quick death. These are some pictures just showing what's happening inside the nucleus when the alpha, beta, or gamma are ejected. That in the alpha particles, the mass goes down by 4. The atomic number goes down by 2. In beta, the mass stays the same because electrons don't really weigh much, but the atomic number actually goes up by 1. That's because what's happening in a beta reaction is actually a neutron is turning into a proton by spitting out its negative part, and so it leaves behind the positive part. In gamma, nothing really happens to the mass or atomic number because light doesn't have mass or charge. All right, you should know something about half-life. Half-life's a measure of the radioactivity of all these elements. It's the time for half of the elements to decay. It ends up that these elements work kind of randomly. Imagine a huge cup full of pennies that you dump out. Well, half will be heads and half will be tails. If you put all the heads back in the cup and you shake it up and you dump it out again, they won't all come out as heads and tails. They won't all come out as heads again. They'll be heads and tails. And so essentially the same thing happens with radioactive particles, that over time they'll decay and they'll slow down in their decay. They follow this really cool exponential decay here. Essentially what will happen is after every half-life, half of them will go away until eventually maybe none are left, but that really takes a long time. The important thing to point out is all of the sample won't be gone after twice the half-life. That it actually takes an extremely long time for all of them to go away. So I have some examples of radioactive particles here. Uranium-235, which is used in nuclear weapon making, has a half-life of 700 million years. Well, if the Earth's been around for 4.5 billion years, it means that not a lot of uranium is still around from when the Earth was first formed. but still enough of it. I mean, you still have a pretty decent amount, since 700 million years means that only about, I don't know, 8 half-lives have actually passed. Plutonium is a lot quicker to go away. Iodine-131, which is found in radioactive waste from power plants and nuclear weapons, that has a half-life of 8 days. You might think this is good. Well, actually, not so much. The shorter a half-life is, the quicker it's spitting out radioactive particles. So it actually can mean it's more dangerous. Luckily, it'll become less dangerous after a very short amount of time. The most dangerous radioactive particles are the ones that have their half-lives on the order of years, because they're going to stick around long enough to keep spewing out radiation for the foreseeable future. But they're quick enough half-life that you're not going to want to be around them because they're spitting out particles relatively quickly. All right, a little something about how we get that uranium-235 for bombs and nuclear power plants. In the ground, uranium is found in rocks, and it's found in mostly 2 isotopes, uranium-235 and uranium-238. Well, uranium-238 is a dud. It doesn't really do anything. You can make plutonium from it, but it won't be used directly to make bombs. We need to get the uranium-235 out. So the way we do that is we process the rock to make pure uranium oxide yellow cake. That's, by the way, the reason we went to war in Iraq, was because we thought Saddam Hussein had yellow cake. You put in a little hydrofluoric acid, and it makes it into uranium hexafluoride, which is a gas. And then you can either centrifuge it, like Iran is doing right now, to separate out the 2 isotopes, or you can put it in some sort of other apparatus to try to separate out the 2 isotopes by mass. And what you do is you get more uranium-235 after doing that. The deal is, if you do that enough, you'll get enough uranium-235 to make bombs. You need about 90% of the uranium in a sample to be uranium-235 in order to be able to make a bomb. If you stop at about 5%, you'll make enough to make a power plant. We're most worried about Iran right now getting higher and higher levels of uranium. They say that they're going to stop at low levels, but we don't necessarily believe them. All right, one important thing to point out is uranium is radioactive. So what happens? Well, remember I said that it'll eventually stabilize itself by spitting out alphas and betas, but uranium turns into all these other elements on the way to stabilizing itself. Well, it spits out alphas and betas and alphas and betas. That's what those little A's are, alpha particles, and B's are beta particles. And essentially, it'll take a really, really long time for it to decay. And along the way, it'll spit out a heck of a lot of radioactivity. Uranium itself has a very long half-life. A stands for annum, or years. Billions of years, uranium-238 sticks around. Remember, that means it's really low-level radioactivity. But all the things it turns into are very radioactive. And they also spit out gammas along the way, which is why you really shouldn't sleep with a chunk of uranium under your pillow at night. All right, so it ends up that uranium doesn't just undergo radioactivity. Those special isotopes, uranium-235 and also one of plutonium, plutonium-239, can do this really special thing. They can do something called fission. It's not the same thing as radioactivity. Fission is when you can split the nucleus. Splitting the atom is what fission is. Splitting the nucleus into 2 really big chunks. This isn't just spitting out an alpha or beta. This is cleaving the nucleus into 2. When you do so, you release large amounts of energy. You release more neutrons because a neutron split it in the first place. And you create 2 new nuclei, 2 new atoms. All right, this produces a heck of a lot of energy. Just 1 pound of uranium-235 fissioning produces the same energy as a really big boom. The largest conventional bomb in the U.S.'s payload right now is about 2,000 tons of TNT. When you go nuclear, it scales up really big. By the way, a pound of uranium is something smaller than a golf ball size of uranium we're talking about here. All right, an equation for this, we can see this is a nuclear equation. Uranium-235 gets hit by a neutron and turns into these things. This is what nuclear waste is. It's the extra atoms that are left over. They're very radioactive, which means they have short half-lives to medium-length half-lives. They also make other isotopes like iodine-131, which is bad for your body. It causes cancer when it's absorbed by your thyroid gland. It also makes extra neutrons. So notice, 1 neutron in, 3 neutrons out. Oh, and by the way, a heck of a lot of energy. Well, what that means is that's 1 uranium atom. What happens if you have more than 1 around? Well, here's the first uranium atom that got it all started, and it spit out 3 more neutrons. If there's more uranium-235 around, it splits those in 2, and then it makes even more neutrons. And if you have a pretty good chunk size of uranium, the next thing you know, you have a chain reaction and a big old boom. All right, that's essentially how you make a nuclear bomb. You take a chunk of uranium, you take another chunk of uranium, you throw the two together by making an explosion, and when they come together, they make that chain reaction, that fission, that essentially has enough energy to blow up a city. If you want it to go slow, you pretty much water down the uranium, and you make a pellet of it, and you put it in a fuel rod, and you put it in a power plant right here in the reactor. And when the control rods go in, it slows it down, and when the control rods are taken out, it speeds it up, and that makes heat and electricity that runs turbines, that makes the electricity that we all use to run our cell phones and iPods. By the way, there is a nuclear power plant in Plymouth, so not too far down the road. One important point to point out is you need, remember, 90% uranium-235 to make that, but you only need about 5% uranium-235 to make that. Power plants can't blow up like bombs because they don't have enough uranium. They can, however, melt down. That's a whole other process that we can talk about. All right, so that was fission. Think fizzing like Alka-Seltzer tablet, breaking up. Its counterpart is fusion, fusing things, putting things together. Unlike huge atoms like uranium, which can fission, fusion can only really happen with really tiny atoms like hydrogen. The reason is, you know that nuclei are positive. So if you want to put two positive things together in a very tiny space, you have to cram them together with incredible heat and pressure, like inside the sun or other stars. That's fusion, and that creates energy as well. So we see in the equation here that hydrogen and hydrogen will make helium. That's how the sun works, and it creates energy too. Well, unfortunately, some weapons scientists got the brilliant idea that instead of using fusion on Earth to try to make power, by the way, this is ITER, I-T-E-R. This is a reactor made in France that's trying to do fission for the purpose of safe and reliable power on Earth. This is the United States' project, the Laser Ignition Facility, LIF. We're trying to do fusion in here to make power for people. Instead, somebody came up with the brilliant idea of, well, don't atom bombs make a lot of heat and pressure? Well, yeah. So if you have an atom bomb right there, and you put some hydrogen with it, well, can't the fission from one produce fusion in the other? Well, yeah, and you end up getting about 100 times the boom from this kind of device. So this is a modern thermonuclear warhead, otherwise known as a hydrogen bomb. You put a little hydrogen inside a regular nuclear bomb, and you get a much, much, much bigger boom from the fission creating the heat and pressure to do the fusion of the hydrogen. This is an example of the size of the boom that you get. This is what would happen if a bomb from the Cuban Missile Crisis, which was a 2.4 megaton of TNT equivalent bomb. Remember, it's actually plutonium in this bomb, not TNT, but it's the size of 2.4 million tons of TNT. If that bomb were to land on Boston, essentially the shock wave would destroy every building in this area and then cause huge amounts of heat and pressure, enough to knock down a lot of buildings and set ones out fire outside that area. And then even outside the area, you get radiation effects from people hit by the radiation from the bomb. And over time, the alpha, beta, and gammas caused by the nuclear waste would drift over the villages around Boston, the cities and the towns, and land. And if people ate food or didn't wash their hands, they could get the radioactive particles in their body, which would cause biological damage. Just so you know, the US has actually exploded a lot of nuclear weapons, mostly here in Nevada, in the desert in the 1950s. You might think, oh, we haven't really been affected that much. This is actually a fallout chart of what happened when the dust was carried by the wind across the country from Nevada. Just so you know, one rad here, which is neutral on the scale, is equivalent to about a quarter of the radiation released by the highest station at Fukushima, which was the Japanese nuclear power plant that blew up a couple years ago that everybody was really, really worried about. That's a lot of radiation. In fact, it's about 4 times the natural dose people would get. So actually, there was a lot of radiation that spread over the United States from all these tests back in the 50s. They elevated cancer risk. Fortunately, those tests moved underground after a few years, and so there wasn't as much fallout and radioactive particles spreading across the United States. We got a little smarter, but those tests are part of our legacy, and we really want to try to avoid the amount of nuclear material that gets spread out from nuclear weapons in the future.